Hello, I welcome you all to this another interesting screencast. Blocks A and B have a mass of 7 kg and 10 kg respectively. Using the coefficient of static friction indicated, determine the largest force P, which can be applied to the cord without causing motion. So we don't want to experience any motion to block B, whether uh, tipping or sliding. There are pulleys at C and D. Okay, this problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Benam. Right, so we are dealing with dry friction, and this is the force that resists the movement of two contacting surfaces that slide or move relative to each other. This is a force. Dry friction force is a force that resists the movement of two contacting surfaces that slide or move relative to each other. We are going to be looking at basically three types of problems, or we encounter three types of dry friction problems, three types of dry friction problems. The first one is where we are experiencing no impending motion. Okay. In this particular case, the number of unknowns is less than or equal to the number of the equations of equilibrium. It means we are able to solve the unknowns using the available equations of equilibrium. Therefore, we also need to check for whether this condition is met at the contacting surface, and if this is met, then we are sure that there is not going to be slip. The second type of problem is where we have impending motion. We have impending motion at some points. These are contacting points or surfaces. In this particular case, we are saying the number of unknowns are greater than the number of equations of equilibrium. In this particular case, we also use additional equation from the friction concept, which is F equal to mu n. And of course, those other points, like we said, some points are going to experience impending motion. It means there are going to be some points, other points from the sum, other points that will not experience impending motion. And those ones we also need to check whether there is slip by using this particular equation. F should be less than mu n. The third case is where we have impending motion. This is where we have impending motion at O. This is where we have impending motion at all points or surfaces. Okay. In this particular case, also the number of unknowns, is greater than the number of equations of equilibrium. In this particular case, of course, we use the friction equation mu F equal to mu n. All right. Let's work on this particular problem. There we go. So we're going to draw the free body diagram. So let's do so. I think they are like so. Okay. Like so. Right. And there we go. Like so. So of course we are going to have, let's say we have the weight acting at that point like so. And also this one, let's say we have this weight acting at that point like so. Okay. And then let's say, of course, we do have a force here. We do have a force. And these pulleys, we are saying there is no friction. We are assuming no friction, no no friction at the pulleys. Okay, it's important so that we have the same force there. Since motion is to the right, we expect friction to oppose. Let's say friction is going to be in the opposite direction like so, and let's say the normal force, we have the normal force there, which will also be there like so, and then we have this component like so. All right, and then to oppose this particular force, we are going to have, let's say, a force like so, and then we have a normal force there like that. So let's label this. So this is B, this is A, this is P. Like we said, no friction, so we expect the same force. And then let's call this one as our FB, and then this one we call it NB, and this one again is FB. Let's call this one as FA, this one as our NA, and then we call this as our WB, and this one as our WA. All right. Right, so we have these dimensions. Okay, so these dimensions are given in millimeters. They're like so, and they're like so. And of course, I'll also show this point here, this one, and also show this point here. This. Right, let me label this. So let's call this as 0.15 meters, 0.15 meters. These are meters, and then this one is 0.4 meters. Okay, and then this one, let's call it XB, this one XA. Okay, all right, so let's start the work. First things, let's count the number of unknowns. So we have number of unknowns. This is going to be equal to, we have 1, 2, 3, 4, 5, 6, 7. We have 7. This is XA, XB, NA, NB, FA, FB, and the P. 1, 2, 3, 4, 5, 6, 7. Alright, so we need one more additional equation because the number of equations of equilibrium each one, there are 3, so 2 by 3, that's 6. So we need one equation. Right, the question is to find the value of P that will not cause motion. Of course, not only motion for B, but motion for A also. We want this structure to remain stable, but we want to find the maximum force that we can apply without causing any motion. No tipping over, no sliding. So let's assume the first case we say, let's say the one equation that we need is this mu AB NB, which is equal to 0.3 NB. So let's say this is the equation. Then if this fails, then we'll try the other equation. Okay, so let's go to block B. Okay, let's apply the equations of equilibrium. So say summation of forces. So say summation of forces in the y equal to 0, going up in our reference. Let me just create a boundary there. Alright, what do we have? Summation of forces in the y, we have minus WB. This is type 2 problem where we have some points experiencing bending motion. So WB plus NB equal to 0. And we know that WB is just going to be equal to mg 10 by 9.81, which is equal to 98.1 newtons. Therefore, NB is just going to be equal to 98.1 newtons. Right. Then we have summation of forces in the x equal to 0. What do we have? So we have a P minus FB equal to 0. And then FB we know that is just equal to 0.3 NB. Therefore, our P will be equal to 0.3 by 98.1. So this gives me a 29.43 newtons. Alright, so let's also check the maximum at xb equal to maximum 0. At xb equal to 0.15 meters. So we'll say, let's call this point as, we can call this point as D. So we'll say summation of moments about point D equal to 0, and clockwise being our reference. So we'll have, if xp is equal to maximum, we want to check the maximum value of p. So that gives us a minus p by 0.4 plus w by, that's wb by 0.15. Okay, therefore since w is equal to wb is equal to 98.1 newtons, P will be equal to 0.15 W divided by 0.4, and P will therefore be equal to that's 0.15 by 98.1 divided by 0.4. This is 36.79. Okay, this is 0.5 by 0.15 by 98.1, okay, divided by 0.4, 36.779. So this is another value of P. So we have two values of P. So I'll say 1 and 2. Okay, this is 1. Alright, so now what we need to do is we are just going to transfer this down. So say let's go to block A. We go to block A. So block A will say summation of forces in the Y. Summation of forces in the Y equal to 0. Going up being our reference, we have minus WA plus NA equal to 0. WA is just going to be equal to 7 by 9.81, and this is just going to be equal to 7 by 9.81. This gives us a 68.67 newtons. Sorry, summation of forces in the Y. We have another component. So minus W minus NB plus NA equal to 0. WA is just going to be equal to 7 by 9.81, and this gives us a 68.67, and we already know what NB is. NB is equal to 98.1 newtons. Therefore NA is just equal to WA plus NB. Therefore NA is equal to 68 plus 98.1. We have a 166.77 newtons. Okay, then we have summation of forces in the X equal to 0. Okay, what do we have? We have FB minus FA equal to 0. Okay, minus FA equal to 0. And we know what FB is. FB is equal to 0.3 NB. Okay, and therefore our FA is just going to be equal to 0.3 by 98.1, and this gives us a 29.43 newtons. Alright, there we go. So we need now to check for slip. So say check for slip between A and C. This boundary here. Okay. So let's calculate F max. F max is equal to mu A times NA. We know that mu A is equal to 0.1 and NA is equal to 166.77 newtons. Therefore, F max is just going to be equal to, just do the multiplication, 166.77 by 0.1. This gives us a 16.68 newtons. Right, so FA, which is equal to a 29.43 newtons, is greater than F max equal to 16.68 newtons. Therefore, slip slip will take place between A and C, and we don't want that. Okay, so instead we will again we will instead we assume that the one that is going to experience impending motion is this boundary. So we'll say assume FA is equal to mu A NA. Therefore we are saying let FA just be equal to 0.1 NA, which is equal to 16.68 newtons. So once we make this assumption, then we'll go to block A to do the calculations. Okay, so this is larger. Okay, this FA is larger. It will be larger even for the second part there. They are all bigger, right? If you've looked for P2, it was even larger, right? If you used P2, FA could have even been larger, right? Okay. Alright. So now block A, we are just concentrating on the summation of forces in the X. So just say summation of forces in the X, because in the Y, nothing changes. Block A, so we are just saying FB minus FA equal to 0. Therefore, our FB, and we know that FA is equal to 16.68. Okay, therefore FB is just going to be equal to 16.68 newtons. Then we go to block B. Okay, this is block B. Again, we're just interested in the summation of forces in the X. So summation of forces in the X equal to 0. In the Y, nothing changes. So here we are just saying it's a P minus FB equal to 0. And we know that FB is equal to 16.68 newtons. Therefore, P minimum will be equal to 16.68 newtons. Alright. Of course, there is no need to check for slip between B and A, because we already know the maximum friction at B, alright, because that is what we had initially started with, right? We had said the value that we found there was, what was the value? We found a value of 29.43, okay? Alright, it is by far bigger than this value, right? So we don't expect any slip at between B and A, okay? So this is the minimum value of P that we need so that no motion is caused, no slip and no tipping of B. Okay, so I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.